Hi, this is Pat Kaplo, and I'm solving question number 14 on page 130 in the Giancoli textbook. The problem reads, a sports car of mass 950 kilograms, including the driver, crosses the rounded top of a hill, radius 95 meters at 22 meters per second. Determine A, the normal force exerted by the road on the car. I've gone ahead and made a sketch of the car rounding the top of the curve. And one of the things I think that's important to recognize here is that even though the point of contact that the car makes with the road right up here at the top, right at this point, is part of a larger circle that I've drawn in with these red dashed lines. So even though it's not completing a full circle or a semicircle, for that moment in time, it is going through circular motion. So let's go ahead and write down our given information. We know the mass of the car. The mass of the car is equal to 950 kilograms. We know that the radius of the circle is equal to 95 meters. And we also know that the velocity of the car at the top is equal to 22 meters per second. I'll go ahead and draw a free body diagram here so that we can see the different forces acting on the car. As usual, we have weight acting in the downward direction, and we also know that there's a normal force acting in the upward direction. The interesting thing here to recognize, though, is that the normal force needs to be a smaller force than the weight. There needs to be some sort of a leftover force in that downward direction. I'll write this off to the side. Some sort of a leftover force here, which we know is going to be our centripetal force. In this problem, it's important to recognize that the centripetal force is going to be in the downward or the negative y direction. So we're ready to go ahead and start writing our equations here. We have our given information. We can say that the normal force minus the weight is going to be equal to the centripetal force. It is important to recognize that that centripetal force, based on the way we've drawn the sketch, that the leftover force, that centripetal force, is going to be in the downward direction and therefore needs to be negative. We'll see that comes into play here in a bit. We can go ahead and expand these terms and say that the normal force minus mg is equal to mv squared over r. So now we have our equation, and we're solving for the normal force n. That's what we're trying to solve for. So in order to isolate that variable, we can add the mg term to both sides. So we're going to get n is equal to, sorry, that should have been negative. I forgot my negative sign there. Negative mv squared over r plus mg is equal to the normal force. We're ready to substitute. So now I can say that the normal force N is equal to the mass of the car, 950 kg. I'll put that in parentheses. I'm going to multiply that by 22 meters per second. And I need to remember to square it. All of that over 95 meters. That's the radius of the turn. And to that, I need to add the term mg, or the weight, which is going to be 900. Oops, I'm out of space, so I'll kind of write that down here. 950 kilograms times 9.8 meters per second squared. That's kind of awkward the way this ended up writing here on the screen, but you can see here that when I run that into my calculator, I'm going to get, for a normal force, 4,470 is what I calculate. 4,470 newtons. I'll need to account for significance and end up calling that normal force 4,500 newtons. 4,500 newtons. That's for part A on question number 14. Part B basically asks, what's the normal force exerted by the car on the 72-kilogram driver? Really, in this problem, kind of everything's the same in part B, except this mass that appears here a couple times is no longer 950 kilograms, the mass of the car. It's the mass of the driver. The driver's in the car doing the same turn, radius 95 meters, at the same speed of the car, 22 meters per second. So ultimately, you can just replace 72 kilograms in for those instances where you have mass. And for part B of the problem, for part B, the solution is the normal force of the seat of the car on the driver is 338.8 newtons. That's what I calculated when I put those numbers in. And so therefore, when we truncate for significance, we'd get 340 newtons. 340 newtons for the normal force on the driver from the car seat. And the last question is part C, the car speed at which the normal force on the driver is equal to 0. For this problem, we could add an additional free body diagram here. Kind of like that new tool. And when I draw my forces in, I could recognize here that I always have a weight at the top of the circle, but at that particular speed, we can say that the car is going so fast that all of the centripetal force required, F sub c, is supplied just by the weight. So in this case, that would be where the car tires are barely touching the road. So in order to answer this question now, we've drawn our free body diagram, and we can actually then write our equation and say that the weight at that point is going to be equal to F sub c. And now we're ready to kind of make some substitutions. mg is equal to mv squared over r. And this should start looking familiar. We've seen this a bunch of times here. The masses cancel out. We're going to multiply both sides by r and take the root, and we get v is equal to root gr. We're ready to substitute. G is, of course, 9.8 meters per second squared, and we're going to multiply that by our radius of 95 meters. And throw that into the calculator, and I guess I don't need this piece here. Throw that into the calculator, and I get 30.5 meters per second is equal to our speed at the top of the hill, 31 meters per second once we account for significance. 31 meters per second. And that's part C from problem number 14.